Example, which is also extremely important for complex analysis. So, and it will be again about products. So there will be y to x and z to z. I don't know, y, crow. So here's what they are. Y is real line, and x is let's say r plus, and x is also r plus. And the map is, so suggestively I'll talk about argument r. So the map takes r to the n. So we know that it's bijective, right? So you can take n through. So it's a homomorphism. Now rho. So what's z? Z is S1 unit circle, and T is also S1 unit circle. And the map, suggestively, it takes cosine theta plus I sine theta to cosine. So we talked about doubling the angle, but I'll take nth iteration of the angle. N theta plus I sine of n theta. So, so both are coverings. So you can. So if you see geometrically what happens here, you just wind the circle over itself n times. So it's definitely a covering. When you do winding locally, you just stretch it a bit. I mean, shrink it a bit. But so both are coverings. So this is bijection. This is a covering. So both are coverings. So then we get that the map from S1 cross R plus to itself and this, as we know, also is known as C star. Which takes, so in my coordinates, R cosine theta plus I sine theta to R to the n cosine of n theta plus I sine of n theta is a covering. By what's written on the blackboard over there on top. But what map is this? It's just nth power of a complex number. So this map takes z with this absolute value and this angle to z to the n. So so the proposition is that the map from C star to, I mean, C star, sorry, is C without 0. It's the usual notation in mathematics. So it's a map from C without 0 to C without 0, which takes complex number to its nth power, and it's a covering. Good. We'll use this later. So some coverings are better than others. It will be a slogan. Some coverings are the best. Now, definition. pi from y to x with x path connected is a universal covering. If several things are true. So first of all, it's a covering. Second, y is simply connected. So if you remember, this means that any two paths are path homotopy. So if you have 2 points, then any two paths are path homotopy. So in particular, it's connected to. So, yeah. So why are such coverings better than the others? Here is the theorem, which I will not prove, but in our main example it will be obvious. So theorem, first of all, any path connected x has at least one, a universal covering. Call it pi from x tilde to x. So universal coverings exist. And B, for any other covering, call it rho, such that y is path connected. There exists a map f from x tilde to y such that pi factors as f composed with rho. Okay. I'll illustrate this soon. So, first of all, let me draw this diagram. So we have this x, and we have its universal covering. And we have some other covering. There exists a map like this. I call it f. There exists f such that pi is rho composed with f. And actually this map is a covering itself. So in particular, so continuous of course, f is continuous. And a covering. But anyways, so from this it follows that, so remark, from the theorem B, it follows that any two universal coverings say x tilde 1 of x and x tilde 2 of x are actually homeomorphic. So basically these are homeomorphic. Good. I have stated that. Now, main examples. So, if x is R then x tilde is what? Let's try to digest definitions. So if x is R, R itself is simply connected. It's contractible. Right? I mean, okay, it's star-shaped. You can fix the point 0, and then any other point is connected along the line to the point 0. So it's simply connected. And in view of this theorem, since the universal covering is unique, x tilde is R itself. Okay. If x is complex numbered, then x is, complex numbers is star-shaped. So it's simply connected. So it's universal covering of itself. Okay. If x is S1, then what's its universal covering? We already had it on the blackboard. So it should be a covering from a simply connected space. I mean, we had this map from R to S1. So then R to S1, which takes theta to cosine theta plus I sine theta, is the universal covering. Check. Is it a covering? Yes, we checked that. Is R simply connected? Yes. So then this is universal covering. In view of my theorem, it's a good candidate and it's unique, so it's a universal covering. So then the next example, yeah, it's still the main example, of course. Let's take x equal to c without 0. Looking for universal covering. X tilde is c, yes. And the map, pi, takes, so from x tilde to x, so from c to c without 0, of course, takes z to exponent of z. So the map we've been studying all this time, like a typical holomorphic map, is the universal covering map for C. Now let's check the universal. So there was this universal property, this one. So let's check it in this second example, because I think this illustrates a lot. So we have the C, and then the universal covering, so exponential map to C without 0. Then we had another example of a covering. C without 0 maps to itself. Z goes to Z to the end. So this is universal covering. This is just a covering. There should be a map like this, so that it would be commuting. Can you cook up a map like this? So this is F. That's this diagram. This is O. I don't think there's anything to be scared of. So it's an equation. Exponential of z equals something, and then to the n. F of z to the n. Can you write this F. Yes. Like this. So this map F is X of Z over N. So in this sense, this map is universal. Whenever you have some other covering, there's always a map like this, such that the composition is very unique. So this illustrates, so it's illustration of universal codes. Good. I think it's time to mention another very easy property. So this is a remark. Let phi from y to x be a covering. And let U be in X open. Actually any, but open is good enough. It follows from the definition that the map from the preimage of U to U is also a covering. So what do you need to check? For every point, its preimage is discrete, but this is true for even bigger space. For every point, there's a neighborhood whose preimage is disjoint union of the same neighborhoods. Yeah, it's still true. Good. Now we will talk about an important issue. So the topic, maybe it will not be the best title, but it will be like this. So sections of coverings and lifting paths along coverings. Great. So, first of all, definition. Let phi from y to x be a covering. Then its section, a section of phi defined on some open U in X, open, is a map, well, a continuous map, S from U to its preimage, such that phi composed with S is identity. Now, for example, I can now define what logarithm is. So, definition. Logarithm of a complex number defined in some open U inside C without zero. This is simply a section of the universal cover defined in U. So, as we know, there is no holomorphic logarithm everywhere. So, remark. So, since both C without zero and C are in complex numbers, we can talk about holomorphic sections. S from U to complex numbers, and such will be this will be holomorphic logarithm. So what we know already is by Kashikhin there is no holomorphic logarithm defined everywhere. And we'll see that by choosing proper open subset in C without zero, we will define such logarithms. So as I said, by definition, logarithm is a section defined on a subset. So this subset will be important datum to define logarithm. Good. So same about, so we can say the same things about root functions. Good. So now let's talk about extension, about lifting of paths. We say, so let phi, this is definition. Let phi from y to x be a covering. Let's say that y is path connected. So a good example would be when y is universal covering of x. Then suppose that we have gamma from 0, 1 to x, a path, a continuous path. Then gamma tilde from 0, 1 to y is lifting of gamma. If, well, we can go from 0, 1 all the way to x, or first to y, so this is gamma tilde, and this is pi. So if pi composed with gamma tilde equals to gamma. So this is the definition. Now, here is the theorem, which I will even try to prove. Suppose we have a universal covering. A universal covering. Actually, any covering doesn't need to be universal. Just y should be connected. A covering of x. And suppose that we have here a point x node and a point y node in x, in y. And there's a path, so we have a path gamma 0, 1, 2 x with gamma of 0 being x node. There exists a unique lifting of gamma, so gamma tilde, from 0, 1 to y, pi composed with gamma of tilde equals gamma, and gamma tilde of 0 equals y naught. So we just need to fix the beginning of the path, and the rest of the path just is lifted. So you should think about it like this. So there's this x, there's this y above, which locally has many pieces. So there's x node and starting path, and we'll fix its pre-image, y node. Then, having fixed this, we can start lifting the path, and we'll lift it uniquely. So uniquely. Okay, so let me hint the proof of the theorem, because it's another way to explain many things in the book. Good. So hint of the thing. So by definition of the covering, there exists, so by definition of the covering, there exists a neighborhood U of x node containing x node open such that well, pre-image of x node is discrete, and pre-image of U of x node is homeomorphic, isomorphic to pre-image of x node times u of x naught. So it's disjoint union over y phi of y equals x naught of the same neighborhood u of x naught. So there exists a unique neighborhood of them, so p's, connected p's, containing y naught. So it's y naught times u of x naught as a connected component inside preimage of u of x naught. Very good. Then let's take a look at this picture. We have this u of x naught, and above it we have another copy of the same thing. So it's around x naught, and there's another copy of the same thing around y naught. This is y naught times u of x naught. Well, and we have this path which starts here. So there's 0, 1, which maps, and it starts here. So so choose S, a section of phi on u of x naught. So S goes from u of x naught to y naught times u of x naught. Well, it's, I mean, phi goes there, and S is just its inverse. I mean, by definition, this piece and this piece were homeomorphic. There's inverse. So I chose it. So take epsilon so that the interval, so gamma of 0 epsilon is inside u of x naught. So define gamma tilde on 0 epsilon by gamma tilde equal gamma restricted on 0 epsilon composed with S. So that's what I drew here. There's a little part of interval. It starts as a path, but I have a section here, S, so I can start this path here as well. Well, and then proceed in the sense that, so I have the beginning of the path, proceed, meaning that you take T1 on this 0 epsilon, and x1 being gamma of T1, where, so take u of x1 and so on. So geometrically, I have this path starting from x0, and already here I have lifted the path upstairs. Then I choose the next point, and I lift the path in some neighborhood of it. Then I choose the next point, and I lift the path here. I proceed, And going all the way, I use compactness of the interval to prove that you can do it infinitely many steps. So use compactness of 0, 1 to show that the procedure ends. The procedure is fine. It's fine. So, good. There's one more thing which is, so I won't prove more of this theorem, although on Thursday we'll see that exactly the same consideration proves the existence of branches of argument, of logarithm, and so on along paths. So it will be always local construction, and then you cover the whole path with neighborhoods where it works, and then you prove that you can infinitely many of them. Generalization. Of this theorem. So this is another theorem. Let gamma 1 and gamma 2 be path homotopic paths in X. So it means that gamma 1 of 0 equals gamma 2 of 0, gamma 1 of 1 equals gamma 2 of 1, and then there's, so both of them are maps from 0, 1 to X. And then there exists a bigger map H from 0, 1 squared to X with H restricted to 0, 1 times 0 is gamma 1, and H restricted to 0, 1 times 1 is gamma 2. So they're path homotopic. And suppose that we have a covering y to x, a covering. And by the previous theorem, we have two lifts, gamma 1 tilde, gamma 2 tilde, two lifts of gamma 1, gamma 2. So gamma I tilde go from 0, 1 to x, to 1. Both of them start from the same point. Gamma 1 tilde of 0 equals gamma 2 tilde of 0. It follows that they are homotopic. There exists a lift of homotopic, H tilde, lift of homotopic. So this is a big theorem, but one corollary from this big theorem is corollary. Since gamma 1 tilde and gamma 2 tilde are path homotopic, it follows that the value at the end is also the same. Path homotopy looks like this. You cannot do it like this. Right? So then gamma tilde 1 of 1 equals gamma tilde 2 of 1. So in a way, it's a very strong statement. So we have this x, and we have a path here, and another path, and they were homotopic. And then there was a point where we wanted to start in y. So y had locally many components, globally maybe not. And then there were two lifts. So this is a lift of one of them, and this is a lift of the other. In principle, they could end in different points. But the theorem says that this is not possible, and there's a homotopy which basically tells us that the image of one is the same point, and it maps here. We will use all this on Thursday, because believe me, what we talked about in this particular example, when y is c and and x is c without 0. So then from this behavior with respect to paths, we will derive existence and properties of logarithm of nth roots of z, and so on. Because they are exactly sections, and we'll see how. Maybe I should end this this lecture by giving a definition. Let G in C be a domain a multi-valued holomorphic function on G is simply a holomorphic function on the universal covering G tilde 2G. So we have this universal covering in a function which is ordinary holomorphic function. But since this map is not invertible, you cannot say that this is a function here. Instead, it's multi-valued because for each point here, you need to choose its preimage and then evaluate the function. So you cannot realize it as a single-valued function from here to here. Now, choosing a value or a branch of multi-valued function is choosing a subset here for which you can take a section. If you take a section, then maybe I should explain this before the end. Choosing a branch of a multi-valued function. So we have this G, we have G tilde. This is universal cover, and this is our function. Now inside G, maybe above. So inside G I have some open U on which there is a section. So this is So section of pi. So choosing a branch is finding such an open subset for which a section exists and choosing this section. So after that, you just can go like this, and this will be your function. But since, in general, globally such section doesn't exist, there's no global function defined on G. It's only a multi-valued function. So whatever you learn in this course about logarithm, about roots, about arcsine, whatever, it fits this scheme that you have some subset where the function cannot be inverted. You take a smaller subset and choose inverse for universal covering, and then you apply. Good. Let's stop here. I think I should stop scaring you. So all